Okay, video 4, magnetic questions continued. I have a question here for you. Question number 3. A 250 turn coil has a reluctance of 5,000 amp turns per Weber and a flux of 50 milliwebers. What current is required to pull the plunger up? So I've drawn a standard solenoid. You'll find these in doorbells, contactors, relays, standard solenoid. The principle behind this is that as current flows in through here, it is going to create an electromagnet within this steel material here, this iron, soft iron material, and this is a spring, and that spring is going to resist a little bit. But when this becomes an electromagnet, we're going to determine how we've got a north here. So that's the first thing we want to do. So is when this becomes energized, it becomes a magnet. This plunger pulls up, and this makes contact, closing the contacts. So the first thing you want to do is determine the polarity of your pole pieces. And I've written the north in here just to show you, but you're going to take, with your left-hand rule for electromagnets, you're going to take your hand, wrap it around this coil. So you're going actually around. You're going in behind this coil here, like this, in behind, and then coming back around. So your fingers are going to wrap around this, and your thumb is going to point to the North Pole. And of course, well, this would be the south. So this would be the north, and this would be the south over here. So now we have the north and the south pole. So we've done that. So check. Next thing we want to do is take a look at what we know. We know we have 5,000 amp turns per Weber. That was in the question. We know we have 250 turns. So we've got that. And we know that our flux is 50 milliwebers. And on your formula sheet, you will see force magnetic being equal to flux times the magnetic reluctance of material. So I've just put that into a handy-dandy little triangle formula. So now you can find your flux is a force magnetic over your reluctance, or your reluctance is a force magnetic over flux, or the force magnetic is equal to your flux times your reluctance. So that's kind of easy. We can do that. So let's take a look here. We want to find out what our force magnetic is here. And so if we're using this, our force magnetic equals our flux times our reluctance. So we've got a force magnetic 50 milliwebers, which is 0.05, times 5,000 amp turns. So 0.05 times 5,000 amp turns gives me 5,000 amp turns gives me 250 amp turns. So 5,000 reluctance. Sorry. So now I've got 250 amp turns. That's my force magnetic. So I can write that down there. 250 amp turns. And now we look here, and we've got saying that the force magnetic is equal to the flux times the reluctance. The force magnetic is equal to flux times reluctance, so we know that. The force magnetic is equal to the flux times my magnetic reluctance of the material. And we know that over here, we know that the force magnetic that we discussed earlier is equal to my amperage times the number of turns. So we can put that in a little triangle to help us understand that, where I can get my number of turns divided by is equal to force magnetic divided by my amperage, or my amperage is my force magnetic divided by my number of turns. So I can say, well, what is it we're looking for? The question is asking, what is my amperage going to be? So my amperage is going to be equal to my force magnetic over my number of turns. And we know that my force magnetic is 250 amp turns, and my number of turns is 250 turns. So I'm going to have a total value of current of 1 amp in this circuit. Continuing on, I want to take a look at a concept called inrush current. So in the last question, we had an air gap that had to close. So it meant that there was a very high reluctance to magnetize that metal within that electromagnet. But as soon as the current starts to flow, it becomes an electromagnet, and we get the electromagnet, that plunger closes. when that plunger closes, we actually get a decrease in the amount of reluctance because it's no longer as reluctant to become magnetized because it's already magnetized. So what ends up happening is that you get a drop in the amount of current. So in other words, it takes more current to close that plunger initially than it will to just run it on its normal, steady, normal current condition. And that increase in the amount of current to get that plunger to close is called inrush current. So I've got a little drawing here, and the inrush current here, you can see this is my inrush here. So this is the normal current operating condition here, and this is the inrush portion here. So if we look at this, we've got a much more current in order to try to close that air gap. And as you can see, it spikes and then it drops very, very quickly. And that's a result of there being a decrease in the reluctance of that material. So let's take a look, let's expand on that question again. Let's take a look at this question here. So as a result of the plunger closing after the inrush current is settled, the reluctance of the material will greatly decrease and the circuit will require less force to hold it in place. So, pose this question. Assume that resistance in the last question has dropped from 5,000 amp turns per Weber to only 625 amp turns per Weber as a result of the air gap closure. Find out what the new current will be. Okay, so now we have 635, should be 625. So I'm going to say is 625. This is 635, so 625. 625 amp turns per Weber. Okay, so I have 625 amp turns per Weber. It's gone from 5,000. The reason it's dropped so much is because of that inrush current has dropped out because the reluctance is considerably lower. So 625 amp turns per Weber for reluctance. So the first thing we want to do is, well, we know that my force magnetic is going to be equal to my flux times my reluctance. So we can say, okay, well, my force magnetic is 625, my reluctance is 625 times 0.05 Webers. So 625.05 is 31.25 amp turns, so a significant decrease. And then we look and go, okay, well, I know that my force magnetic is equal to my amp turns times my current times my amp turns. So I can say, well, that my amps must be equal to my force magnetic over my number of turns. So my force magnetic, we just calculated at 31.25 amp turns, divided by my number of turns, hasn't changed. 250 is going to give me with a holding current of 0.0125 amps, or 12.5 milliamps. So, 0.125. So 125 milliamps, not 0.0125. So 0.125, 31.25 divided by 250. So we got 125 milliamps. So this is called the holding current. So the amount of current that would be required to keep that plunger in place after it has been de-energized as a result of the reluctance dropping significantly.